Okay, so we got a p-value equals 0.002. So we rejected the null hypothesis, right? Here's the thing. Remember, at the end of this, we still don't know who's different from who. We just know that somebody's different, right? At the end of this, what you want to do is they're going to be sort of like little paired t-tests, right? They're often called contrasts. And you want to do that in order to figure out what your actual, like which group actually differs from which other group, not just whether some group differs from some other group, right? And so you want to do a little bit more after you do this. These are called post hoc tests. And in a lot of ways, they're very similar to, not paired t-tests, they're similar to t-tests, right, where you look at pairs. There's one change. They change the sort of p-value that you're looking for. But you want to do the post hoc tests afterwards and to do all the little comparisons so that you can figure out who's different from who. But you're only allowed to do a post hoc test if you rejected the null hypotheses, right? So you're not allowed to do a post hoc test if you haven't rejected the null hypotheses. That's why we can't just skip to this step from the very beginning. So first thing you need to do if you reject is do post hoc tests. Second thing you need to do is find the effect size. In the case of an F-test, you're not going to find like Cohen's D or Hedges G. You're not going to find that kind of effect size. You're going to find what's called eta squared. Eta sort of looks like a n squared, right? And an eta squared is going to give you an idea of the effect size. Okay, now let's go on to example 2. So also the data is provided in your download. A pharmaceutical company wants to know whether a new drug has a side effect of causing patients to become jittery. 3 randomly selected samples of patients were given 3 mild doses of this drug, 0, 100, 200 milligrams, and they were also given a finger tapping exercise. Does this drug affect this finger tapping behavior? Well, this one I didn't, format really nicely for you because I want you to sort of figure it out as you go, but don't worry, I'll do this with you. So first things first, omnibus hypothesis, right? Omnibus hypothesis. And that's that all 3 dosages are the same, right? So mu of dosage 0, equals mu of dosage 100 equals mu of dosage 200, right? And the alternative hypothesis is that mu of the dosages are not all same. Okay. Step 2, alpha equals 0.05. Step 3, decision stage. How do we make our decision to reject or fail to reject? First, you want to draw that F distribution. Could color in that or leave that alpha equals 0.05. That's the error rate we're willing to tolerate. Now, what is our critical F? In order to find our critical F, we're going to need to know the degrees of freedom for between and degrees of freedom for within. So if you go to example 2, the worksheet for example 2, so you can see that, example 2, then you could see this data set. Now usually this is not the way data is set up, especially if you use SPSS or Stata or some of these other statistics packages. Usually you'll see the data for one person on one line, just like this, just like example 1. The data for one person, their ethnicity and their photos are on one line. You'll rarely see this, but you may see this in textbooks. So I do want you to sort of pay attention to that. But here in the problem, it did say different people were given these different dosages. So you could assume each square to be a different person. So different person, different person. Okay. So we're on step 3, decision stage. And in order to figure out our critical F, we need to know the degrees of freedom between and degrees of freedom within. It's not so pretty anymore. It just takes a long time to do that, to put all those little fancy things in there. But it's pretty easy. All right, so degrees of freedom between, in order to find that, it would be really helpful if we knew the K, right? How many groups, right? And there are 3 groups, 3 different drug dosages. So it's K minus 1, degrees of freedom 2. In order to find degrees of freedom within, we need to know N total, right? How many total data points do we have? And we could easily find that in Excel by using count and selecting all our data points. So there's 30 people, 10 people in each group. So that's going to be N total minus K. That should be 27, right? Once we know that, then we could find our critical F. And we use F in probability of 0.05. Degrees of freedom for the numerator is going to be degrees of freedom between. Degrees of freedom for the denominator is degrees of freedom within. And we get 3.35 as our critical F. Note that this is a larger critical F than before when we had more data points. We had like 90 data points in the other example. And because of that, that brought down our critical F. All right, now let's go to step 4. In step 4, we need to calculate the samples F, as well as the p-value. Let's talk about how to do F. Here we need the variance between, divided by the variance within. How do we find the variance between? Well, that's going to be the sum of squares between divided by the degrees of freedom between. How do we find sum of squares between? Well, remember, the idea of it is going to be the mean for each group, the distance from that mean to the grand mean, square that distance, right? Weight that distance by however many n's we have, and then add them all up, right? So, in order to get that, I'll put it down here. Oh, well, why don't we put in the other stuff too? The variance within, that's going to be the sum of squares within divided by degrees of freedom within, just so I know how much room I have to work with. Okay, so first it might be helpful to know which thing we're talking about. So dosage, right? So it's 0, so D0, D100, and D200. Those are our 3 different groups. What is the N for each of these groups? What is the X bar for each of these groups? What is the grand mean for each of these groups? And then we want to look at N times X bar minus the grand mean. And we want to square that. Excuse me. And then once we have that, then we want to add these up. And so I'll put sum here just so that I can remember to add them up. Okay, so the n's for all of these are 10, right? We already know that. And let's find the x bars. So this is the average of these, right? And then the next one, it's the same thing. Oops. We know it's going to be the same thing, the average, except for column B. And then the next one is average again, but for column C, for 200. How do we find the grand mean? We find the average of just everybody, the whole shebang. Right? And we could put a little pointer so that they all have the same grand means. Now we could calculate the weighted distance squared for each of these groups, right? Each of these group means. So it's n times x bar minus the grand mean squared, not square rooted. All right. And then once you have that, you could just drag it all the way down. And here we sum these all up. We sum these weighted differences up. And we get a sum of squares of 394. Right? And we already know the degrees of freedom between groups. So we could put this in, divide it by this number. And we get 197. Now let's see, is that going to be bigger or smaller than the variance within, right? And in order to find the variance within, it helps to just sort of conceptually remember, okay, what is the sum of squares within? That's the sum of squares for each of these groups, right, from their own means. And so the sum of squares for each of these dosages are going to be, and I'm just going to use that shortcut, the variance for this set multiplied by 9, right? Let's see if that, oh, I put 8. Multiplied by 9, that's n minus 1, right? And I'm just going to take that, and I'm going to say, do that for the second column as well as the third column. And once I do that, I just want to sum these all up, and I get 419. So now I have my sum of squares within. I divide that by my degrees of freedom within, and I get 15.53. And even before we do anything, we could see, wow, that variance between is a lot bigger than the variance within. So we divide, and we get 12.69, 12.7, right? And that's much larger than the critical F that we set. What is the p-value for this? We use f-dist. We put in the f value we got. We put in the degrees of freedom between, degrees of freedom within, and we get a p-value of 0.0001. So we're pretty sure that there's a difference between these three groups in terms of finger tapping. We just don't know what that difference is, right? So step 5 would be reject null. And once we decided to reject the null, then you would go on to do post hoc tests as well as calculating effect size.